This simulation is going to help us to understand the concept of momentum and how it relates to collisions. So first, let's just start off with two things that we're already familiar with, and the first one is mass. So I can increase the mass of billiard ball 1 here, and I can also decrease its mass, and that's measured in kilograms. And the next thing I can do is I can change the velocity of mass 1. So let's say I give mass 1 a small velocity. So this is pointing to the right. So this is going to have a small positive velocity. So if I let this thing run, it's moving slowly into the right. So it's going to have a small positive velocity. And let's just reset this. Now let's say that mass 1 now is going to have a large velocity to the right. So let's see what this is going to look like. So you can see there it's moving faster. So we have to take into account the velocity of an object. So you can ignore that collision for now. So here, this is going to have a velocity to the left. So to the left is going to be a negative velocity, and to the right is going to be a positive velocity. So this is going to have a positive velocity to the right and a negative velocity to the left here. So those are the two terms, mass and also velocity, which can be positive to the right and negative to the left. Now we're going to introduce a new concept, which is a concept of momentum. And that's represented here by this yellow arrow. So momentum depends on the two things that we just talked about. If I increase the mass of an object, this momentum is going to increase. So the bigger the mass, the bigger the momentum. And the smaller the mass, the smaller momentum, the smaller the momentum. And then also, if I increase the speed of mass 1, the bigger its momentum is going to be. So the bigger the velocity, the bigger the momentum. And also, momentum has a direction. So if to the right, momentum is going to have a positive value, and to the left, momentum is going to have a negative value. So it depends on the velocity. So now let's look at a collision. So we have mass 1. It's moving to the right with the velocity. Let's call that one v1 before the collision. And let's say that mass 2 is stationary before the collision, so its initial velocity is going to be 0. And let's also look at their momenta. So notice that mass 1 has a momentum because it has a velocity, so it has a yellow arrow. And mass 2 has no momentum because it has no velocity. And that's and in this case here, that we're going to look at when they're going to just collide and bounce off of each other. So this is going to be a general case here. So they're moving towards each other. And when they collide, you see that they fly off with different velocities in different directions and also a different momenta. But there's something that's always going to be true during collision. So let's just redo this one again here. So the individual velocities and the individual momenta for each object can change during a collision, but there's something that is always going to remain the same. And what's going to remain the same is the total momentum. What that means is that you're going to calculate the total momentum before the collision. So calculate the momentum of mass 1 and calculate the momentum of mass 2. Add those together, that's going to be the total initial momentum. And then you wait until after the collision. And then after the collision, what you do is you calculate the momentum for mass 1 and calculate the momentum for mass 2, add those together. That's going to give you the total final momentum. And what you're always going to find is that the total initial momentum is always going to equal the total final momentum. So we call that conservation of momentum. Now let's look at an application of the conservation of momentum. So here you're going to have is two objects. They're going to be moving towards each other. Mass 1 is going to be moving forwards with a velocity v1. Mass 2 is going to be moving backwards with a negative velocity v2. And since these are going to be before the collision, let's call for the first one v1 initial, positive v1 initial. And for the second one, we'll call that one negative v2 initial. So velocity of v2 before the collision, and it's negative because it's going backwards. So in this case, they're going to collide and they're going to stick together. So let's see what's going to happen. So they collide and stick, and what you notice is that they're both moving backwards at the same velocity. The reason why they're moving backwards at the same velocity is because they're stuck as one common object, and because of that, they both have the same velocity after the collision. So you would use conservation of momentum to calculate that final velocity after the collision. In this case, you can call that one v final for both objects after the collision. And also, because they're both moving backwards, the final velocity after the collision should be negative. Let's look at another case. So in this case here, let's say that they're going to collide and they're going to stick together. But here they're going to, let's say that one of them is stationary. So that means that the initial velocity for mass 2 is going to be 0. And let's see what happens when they collide and they stick. So again, they collide, they move together as one common object. So after the collision, they both move off with the same final velocity. So they're both going to have the velocity vf final for both objects. In this case here, they're both moving towards the right, so they're both going to have the same positive final velocity, so positive vf final. And you would use conservation of momentum in both cases that we just looked at to find a final velocity after the collision.